Okay, let's now return back. And if you remember, we reached this condition and we say that we have two conditions. The first condition is a material condition to ensure that the material have a gaining, or the material has a gaining effect where N2 should be greater than G2 over G1 times N1. And the second condition was related to the system where we ensure that the total surviving factor is greater than 1, and then we have a overall amplification coefficient, or that the amplification is dominating with respect to losses represented in R1 and R2, as you can see. So this is a general equation. However, let's now go into details. Let's now go deeply to this equation. Here, this is what we can call mathematically an inequality equation. We have a condition that this gamma should be greater than this value. But please remember, as we mentioned in part number 1 of this lecture, that gamma is a function in the frequency. It's a frequency dependent function, because here you have lambda square and here you have the line shape function, which is a frequency dependent. However, the right hand side of this inequality, which we call it alpha, is a constant, because LG is the distance between the two mirrors, or the length of the gaining medium. It's a constant. R1 and R2 is the reflections of the mirrors. It's constant. So this is a constant too. So what we are making here is that we are comparing. In the left hand side, we have a frequency dependent function, and in the right hand side, we have a constant. So in order to demonstrate this, we can use here some graphical demonstration. So this is a graphical demonstration. Assume that this function, this somehow bell-shaped function, represents a gamma, or the gaining function. And this is the constant alpha. That means that the condition is not applied for all the frequency values on the x-axis. It will be only applied if the function gamma is greater than this alpha constant. In this region, here mentioned, or what we call the region of a possible oscillation, in this region, only in this region, you can have a gain. However, when the frequency is greater or smaller than this region, the amplification gain or the oscillation gain will not happen, because in this case, alpha will not be greater than, or sorry, gamma will not be greater than alpha. So here we can have what we call the region of interest, the region at which you ensure that this condition occurs. So let's now return to the previous lecture. In the previous lecture, you have we have determined what's called the transmission curve, if you remember. The transmission curve, I will try to get it somehow if we can. I hope we can. In the lectures, let's do it now. In this, it was the optical cavity lecture, my dear students, and here. Okay, this is perfect, and now I hope I can switch to this lecture. Okay, so hopefully you can now see this transmission curves is here. If you can see, I hope you can now see it. So this is the transmission curves we concluded from the cavity lecture. In the cavity lecture, we say that we have a transmission. This transmission can reach 1, and this transmission occurs at a certain resonance frequency. Here, the x-axis is not the frequency. Here, the x-axis is the gain axis. So, as you can see here, the x-axis is the gain axis, and then This is a transmission curves at resonant frequencies. The value of the frequency was C over 2ND, if you remember, and we call this distance is a free spectral range. But please remember that these curves were plotted for what we call a resonance, or sorry, a lossless cavity. I mean, this cavity, the cavity we study in chapter number 4, was either an amplification nor a attenuation cavity. You only have this, if you remember here, you only have this exponential term. I think we have it somehow, this exponential term, which represents the propagation, and that's all. Now, what if this cavity turns to be an oscillating cavity? I mean, you replace the medium between the mirrors to be a gaining medium. Let's now return back to our main slides. So here, and let's now turn on the laser. Okay, so now the medium is gaining medium. You still have a transmission curve, but what will happen is something like that. This is the transmission curves you usually, or you used to have in the previous lecture. Basically, these transmission curves should have the same transmission value, which can be equal to 1 if you satisfy the condition. But some of these frequencies will be within the region of interest of our gamma. So these amplitudes will start to increase, will start to be amplified. And some other frequencies will be outside the region of interest. So these will be attenuated, because in this case, gamma will be smaller than alpha, and then you will have an overall attenuating performance. And within this, outside this resonance, you will have this amplification effect, and the resonance frequencies will be attenuated. So, as far as you are progressing inside the cavity, resonance frequency within the region of interest will be magnified, will be amplified somehow. And other frequencies will be decayed till they reach zero. So you select a certain frequencies, and then you start to amplify these frequencies. Now, what if you are designing a monochromatic laser? You need only a one frequency. Then you will adjust your cavity so that you will have only one resonance frequency in this area, and all other resonance frequency is outside this area. You can do so by two effects, actually. First, by narrowing the bandwidth of this gamma function. Second, by increasing the free spectral range between each two resonance frequencies. If you remember the free spectral range, which is C over 2 and D. Now you will have only one selected monochromatic frequency, and this monochromatic frequency will be the only frequency that will be magnified or amplified in the cavity, and other frequencies will be attenuated. Okay, that's the concept of the amplification or the oscillation. But now we have a very important question. As we know that this cavity is somehow a periodic process, so you have photons go here and there, and then this process, this round trip journey will be repeated, and time will be repeated something maybe tends to infinity many times. So based on this theory, this selected frequency will be magnified or will be amplified each time by each round trip by these factors which called gamma. Okay, that's basically something good. Oh, we need to have it as much larger as possible. However, it doesn't make sense that this amplification process will tend to infinity. This is not a physical process. You know that any force should have some saturation, not increase till infinity. It should be saturated somehow. However, as we mentioned here, by each round trip, this gamma factor, which is greater than 1, will increase or will be multiplied by the selected frequency, and then the selected frequency will increase more and more. So this is an endless process based on this example. So what we are trying to do now is to show, is this really an endless process, or it's a process where we have a saturation limit. In order to do so, we will start to work on the basic model for a laser, which what we call the 3-level laser. Okay, this is the 3-level laser. Back maybe 2 lectures ago, we defined the Einstein coefficient on 2 energy levels, E1 and E2, where we defined the 3 main processes: the spontaneous emission, the stimulated emission, and the absorption. Now we turn to have what's called a 3 energy level system, or 3-level system. Maybe one of the questions that we will try to answer in this lecture: why we need 3 levels? Why we should start designing our laser on 3 level? Or the question in another way, why we don't have a 2-level laser? We should answer actually this very important question during this lecture. However, let's now start. Here we have 3 levels. We call this level as a reservoir of atoms. You know, in the petroleum engineer, we have usual reservoirs. Here this is our reservoir of atoms. This is our stack. Here we have a very large number of electrons. And now we have 2 levels. Let's first try to describe these arrows. As you know, in order to make a stimulated emission and in order to make absorption, we have to have an input intensity. We talk a lot about this input intensity, and we first start with a black body radiation, and then we assume that we will make it a laser, a monochromatic laser, and also we study in the optical cavity that this intensity may be very, very, very small. It may be some sort of noise in order to make the light, or in order to create a stimulated emission. So I believe you already know that you need some input intensity here in order to make absorption or stimulated emission. So this input intensity will act to pump electrons from the energy level 0 to the energy level number 1, and from the energy level 0 to the energy level number 2. We have what's called a pumping rate, where we can call it R1 and R2. And maybe from my point of view, this is one of the main disadvantages of using Verdi, is the repeated terminology. Because we used already R1 and R2 previously, if you remember here. R1 and R2 here are the optical cavity or the optical mirrors reflections. But R1 and R2 here are the pumping rate from the reservoir level or the ground level to level number 1 and level number 2. So please take care when you are using terms. You have to relate the term to the context. When you are talking about an optical cavity, then R is a reflection. When you are talking about the 3-level laser, the R is the pumping rate to energy number 1 and energy number 2. So this is the pumping rate for R number 1 and R number 2 due to the input intensity. If we start with level number 2, for example, you will have the 3 main basic phenomena, or what we call Einstein coefficient. The first is what we call the spontaneous emission. I believe you already know that this is an electron move from the energy level number 2 to energy level number 1 without any restriction. So we have a generated photon. This generated photon is a random photon. maybe have any type of direction, polarization, whatever it is. So it's a random photon. And we have another which calls the stimulated emission. This stimulated emission is restricted that the output photon is coherent with the input photon. So we have one input photon inside and we got two output photons. The two photons should be coherent, should have the same frequency, phase, direction, all these stuff. So that's what we call stimulated emission. And then we have the absorption. Then you have one photon here. This photon is captured by one electron, and the electron move from energy level number 1 to energy level number 2. So this is simply the process that can happen in energy level number 2. But there is also another process, which is the spontaneous emission from energy level number 2 to energy level number 0. So you may have some electron that lose its energy and then it's dropped in one shot from energy level number 2 to energy level number 0, and then we have a spontaneous emission. Now we have to identify two important issues. Maybe you can think about why we don't have a spontaneous, stimulated emission between energy level E2 and the ground level. Here we defined only a spontaneous emission. We did not define the stimulated emission. Why? I believe you can answer this question because, as we mentioned earlier, a stimulated emission is a process where you have two output photons coherent with the same frequency. Knowing that what we incident to this system is a monochromatic source, laser, then the input frequency is E2 minus E1. And in order to have a coherent photon, then the output photon should have also a frequency E2 minus E1. So what the photons that will be generated due to an electron motion from energy level number 2 to energy level number 1 will never be a stimulated emission photons because it will not have the energy E2 minus E1. So the stimulated emission is restricted only to the motion between energy level number 2 and energy level number 1. No other transfer will lead to a stimulated emission. So now we described all the R's from E2. Now what about the R's from E1? We have the relation between E2 and E1 is counted, but we have one more phenomena, which is the probability to have an electron spontaneously, a photon spontaneously emitted from energy level number 2 or energy level number 1 to energy level number 0. So if you have an electron here, this electron is dropped here, then you will have a spontaneous emission photon. Again, it can be never a stimulated emission photon because its energy is E1 minus E0 and not E2 minus E1. So these are all the R's associated to these three level layers. What we are going to do now is we are going to try to write what we can call a rate equation for this system. Previously, if you remember, in lecture number 3, in the atomic radiation, we write our first rate equation based on Einstein coefficient when we say that dN2 by dt is equals to spontaneous stimulated absorption. If you remember, and we do the same for dN1 by dt, if you remember. And actually, we use this to make an analogy with the black body radiation and to extract the ratio between the Einstein coefficient. So what we are going to do now is that we are going to repeat the same process. We are going to start to write a rate equation for the energy level E2 and for the energy level E1. Let's start with the energy level E2. Okay, let's now start to write the rate equation for the two energy levels E2 and E1. Let's start with E2. As you remember, the rate equation starts with saying that dNt by dt is equals to blah, blah, blah. So dNt by dt is simply the rate of a change of the population of these energy levels. So we have to start to think what effects here increase the rate of population. So this will be in the positive sign. And what effects here will decrease the rate of population, and this will be in the negative sign. Let's start with the positive impact. What should increase this population? You will find that you have two terms that increase the population. The first is the injection from the reservoir. So this basically increases the number of electrons or the population level. So R2 is the rate you are pumping electrons from 2 to 1, or from 0 to 1, from 0 to 2, I'm sorry, from 0 to 2. And also the absorption effect from 1 to 2 will increase the number of electrons into. But what decreases the number of electrons into? The spontaneous emission from 2 to 1, which what we call it 1 over tau to 1. The spontaneous emission from 2 to 0, or what we can call it 1 over tau to 0, and the stimulated emission from 2 to 1. These are the three effects that decrease the population on the level E2. So what we will do is something like that. dN2 by dt is equals to, first we have R2, which is the rate of pumping electrons from 0 to 2, minus, here we have the term N2 over tau 2, N2 over tau 2. N2 is the population in 2, and tau 2 is actually the summation of the two effects. Let's now turn to the lecture script to describe it well. So I believe you now see. So here the term 1 over tau 2 is a summation of 1 over tau 2 1 and 1 over tau 2 0. 1 over tau 2 1 is the 1 over tau 2 1 is the 1 over tau 2 1 is the spontaneous emission from 2 to 1, and 1 over tau 2 0 is the spontaneous emission from 2 to 0. So these two terms, the summation of these two terms is included in 1 over tau 2. So N2 over tau 2 is simply the overall spontaneous emission, either from 2 to 1 or from 2 to 0, as you can see here. And also we have, so we have the rate equation. This is in positive because we have the rate, the pumping rate, which is in positive because this is electrons coming from 0 to 2. We have spontaneous emissions. This is in negative. This spontaneous emission can occur from 2 to 1 or from 2 to 0. And then we have this famous term, if you remember, which include both the stimulated emission and the spontaneous emission between 2 and 1. If you remember this famous term, we use it more than one time in our equation, which is sigma I. Sigma is the cross-sectional stimulated emission cross-sectional intensity over the energy over the photon, and 2 minus N1. And here we assume that G2 over G1 is equals to 1, just to make it some sort easier, because basically this equation is minus G2 over G1 times N1. So here G2 over G1 is equals to 1. Just to make this equation more simple. So this is the overall rate equation for the second energy level. Again, we have a pumping rate from 0 to 2. We have a spontaneous emission either from 2 to 1 or from 2 to 0. We have stimulated emission from 2 to 1. We have absorption from 2 to 1. So this is what we do together now. Let's now return back to our slides again. And let's turn now again the laser pointer. And here, this is the equation. No, let's now do the same process for energy level number 1. For energy level number 1, we have also the pumping rate or the injection rate from level number 0 to level number 1, which we can call it R1. What also increase the number of electrons in energy level number 1 is the spontaneous emission from 2 to 1. The spontaneous emission from 2 to 1 will increase the number of electrons in energy number 1. What also increases the number of electrons in energy number 1, energy level number 1, is the stimulated emission from 2 to 1. So now we have three positive terms. You have bumping from 0 to 1, spontaneous emission from 2 to 1, stimulated emission from 2 to 1. Then, what are the negative terms? What are the terms that will act to decrease the population in energy level number 2? Here we have the absorption from 1 to 2, because the absorption means that electrons transfer from here to there, then electrons will decrease in 1. And we have also the spontaneous emission from 1 to 0. So these are the negative terms. Let's now write the equations. Then dN2 by dt is equals to positive R1 of t, the bumping rate from 0 to 1. We have a positive term here, which is N2 over tau 2 1, which is the spontaneous emission from 2 to 1. Again, this will increase. Now the stimulated emission in positive. Here the stimulated emission is negative because the stimulated emission decrease the number of electrons in energy number 2 and increase the number of electrons in energy level number 1. So this term now in positive, which is the stimulated emission, but the absorption is in negative. Makes sense? And finally, you have this term which represents the spontaneous emission from level number 1 to level number 0. So this is generally the rate equation for energy level number 1, and this is the rate equation for energy level number 2. Now we have these two rate equations. Please don't forget that we are still answering the question. Sorry. Does this gaining process is a continuous process till infinity? Does this process is an endless process, or it has some saturation? That's why these slides are named by gain condition and gain situation. So this is what we are searching about. We start with the three energy level. We write a rate equation for energy level number 2 and energy level number 1. Now, what we are going now to do is we are going to start to try to solve these equations. These are two equations with two unknowns, because we will consider that only N1 and N2 are our unknowns, and these are two equations. But actually, this is not a very simple equation because they are two differential equations, not a linear equation. So in order to try to solve these equations, we will do a lot of assumptions. Now we will try to make three different solutions. We will start with the very simple solution. Then we will make it a bit difficult, and then we start to make the exact solution without any assumption. So we will have three cases. Let me say that as a part of your exam, you will be only required to understand the mathematical part of the first solution, which is the most simple one, which with a lot of assumption. But you have to understand the physics and the concept for the three solutions. So you will make it mathematically by your hand in the first case. In the other case, I will just show the mathematics. You are not asked to make the mathematics by your hand, but you should understand the results and why you get or why we reach this result. So let's start again. We are now trying to solve these two differential equations. So let's start with case number 1, which is the easiest case. Sorry. Okay. I'm sorry. Just okay. Now return back. Okay. So let's start with case number 1, which is the easiest case. Again, we are trying to solve two equations with two unknowns. What we will try to assume first, that we will try to assume that N2 is much greater than N1 and tau 2 is much greater than tau 1. Let me stop here and try to make you understand these two conditions. The first condition actually is an old condition. Why it's an old condition? Because we already say that in order to have a gaining material, you should make N2 greater than G2 over G1 minus N1. Now we put G2 over G1 equals 1, so N2 should be greater than N1. But what I add in this assumption that is N2 is much greater than N1. But you have to know that in all cases, in order to have a gain, N2 should be greater than N1. Now it's much greater than 2. Okay. But what about tau 2 and tau 1? Actually, we did not invest a lot of time about taus in general. What is tau 2 and what is tau 1? Now, I can say that tau 2 is the lifetime of the electron in energy level number 2. And tau 1 is the lifetime of the electrons in energy level number 1. So when tau 2 is big, is a large number, that means consequently that electron will stay a huge number of time in this energy level. When tau is a small number, that means that electron will not stay too long time in this energy level. So in order to have N2 greater than N1, it makes sense that tau 2, or it makes sense that the probability for an electron to stay in energy level number 2 is larger than the probability of an electron to stay in energy level number 1. So when tau 2 is large, that means that electron stay a good portion of time in tau 2 and then it moves. When tau 1 is small, that means that electron just reach energy level number 1 and then it's moved to another energy level, either 2 or 0. So that means that the rate is the reciprocal of the lifetime, which actually again makes sense. For example, if I say that we are 10 persons in a room, in every 1 hour, 1 person will leave this room. So the time is large. Accordingly, the rate of our motion is very slow. You need 1 hour to examine a change in the number of persons per room. But what if we are 10 persons in the room and I say that every 1 minute, 1 person will leave this room? Then when the lifetime of the persons in the room is low, we have a very high rate. Each 1 minute, one person will leave. Each 1 minute, 1 person will leave. So the rate is inversely proportional to the time. That's why here we demonstrate the rate by 1 over tau, 1 over tau, 1 over tau. That's why. So N2 is greater than N1 and tau 2 are greater than tau 1 is somehow correlated, because when you make the lifetime of the electron large, that means that the rate is small, and that means that the number of the population is higher. So that's why I need you to understand these two conditions. Now, what is the impact when I said that N2 is much greater than N1? What is the impact of it? Here, as you can see, this is dN2 by dt will not be affected. R2 of t will not be affected again. N2 over tau 2, no problem. And now here we have N2 minus N1. And as far as N2 is much greater than N1, then you can rewrite, oh, sorry, I'm here, I think I have, I'm sorry. I think I should now return, I forgot, I should now return to the lecture script, and also let me turn again my laser pointer. Okay, now I am here. So when you say that the first condition is that N2 is much greater than N1, then you can easily say that N2 minus N1 is automatically equals to N2. So you can get right from this N1 here. So you can rewrite the equation that dN2 by dt equal R2 minus N2 over tau 2 minus sigma I H mu times N2, which is the same equation like this one, but with getting rid from this N1, assuming that N2 is much greater than N1. And for this equation, you can say that dN2 by dN1 by dt equal R1 of t, N2 tau 2, blah, blah, blah. And here, the same process, you can get rid of N1, and then you will have N2 only and this term. So again, this is the second equation. Okay, but what is the gain? What is the simplification? You just get rid of N2 minus N1, you can make it N2. But now, this equation, which is equation number 1, which is the rate equation for energy level number 2, this equation is only now a function of N2. Now, if you remember, the old one, the original form of the equation, was functioned with N1 and N2. By getting rid from this N1, now this equation is only function N2. Now, it's just the time to make the second assumption. Again, the first assumption was N2 is much greater than N1, which is tau 2 is much greater than tau 1. What is the second assumption? The second assumption is that it's a steady state. What do you mean by steady state? I mean that N2, dN2 by dt, and dN1 by dt is equals to 0. You remember the steady state condition. So, by making this dN2 by dt is equal to 0, it becomes very easy. You can have now a very basic linear equation function in N2. You can have N2 in one side and all other stuff in the other side. So N2 is equals to R2 over 1 over tau 2 plus sigma I over h mu. Again, please remember the question. We are thinking why, or does this gaining process is an endless process or not? Let's now return the gain. Please remember that we have now a value or an equation to express N2, which is the population of electrons in energy level number 2. What about the gain? Do you remember the first equation? di by dz equals sigma, or equals to gamma times I. You remember this equation? di by dz equals gamma times I. That's right. So let's now reuse this equation. So di by dz equals these terms times gamma times I. That's right. So you can say that, you can here say that gamma equals to 1 over mu di by dz. Okay, gamma equals sigma N2 minus N1. That's true. Let's make it this first. So I'm sorry. So gamma equals sigma N2 minus N1. That's true. This is sigma, if you remember. And this is N2 minus N1. And we assume again G2 over G1. Again, I think we mentioned it here. Yeah. We assume that G2. Yeah, we assume that G2 over G1 equals to 1. So simply gamma equals to sigma N2 minus N1. And as we mentioned, N2 is much greater than N1. So you can say, okay, gamma is equals to sigma times N2. Now you have gamma, sorry, now you have N2, then you can have gamma. So simply gamma equals to sigma times what you reach here to accept. So sigma equals gamma times R2 tau 2 over 1 plus sigma tau 2 I mu over h mu. So this is very simple, as you can see. This is the term to express gamma. Okay, again, where is the issue? Now, this is gamma, and this is sigma. But please take care. Gamma now is not only function in frequency, but gamma is only function in the intensity. This I mu. This is the input intensity. So to make it easier, we will collect this constant sigma R2 tau 2 and we will call it gamma naught. And we will collect the term sigma tau 2 over h mu and we will collect it IS, or the saturation intensity. Then you will have these two very important equations. Gamma equals some constant, gamma naught, over 1 plus I of mu minus IS. Okay. Why this equation is a very important equation? Now, return back to the cavity lecture. When we start that, we say that in order to excite the cavity, we need a very small intensity. So I is very small in the beginning, tends to be 0. Hypothetically is equal to 0. So if I say that I tends to 0, then this gamma will be equals to gamma naught, which is sigma R2 times tau 2. It's a constant, no worries. And if we find the conditions, then this constant is greater than 0, and then actually is also greater than 1, or greater than alpha, if you remember, and then it's an amplification. No worries. After a while, let's assume that I mu, as far as you enter the cavity, the intensity will start to increase. This is normal. Then what if gamma, what if I of mu reaches to be equal to IS, for example? Then you will have gamma equals 1 plus IS over IS, which is 1. So gamma now is equal to gamma node over 2. So when the intensity increase, the gain coefficient decrease. Okay, when I of mu equals to 2IS, then now you will find that gamma equal gamma node over 3. Then the gain increase again. So the gain increase, the gain coefficient increase. So this equation says that our gain coefficient is not constant. Our gain coefficient is inversely proportional to the intensity. In the beginning, when the intensity is very, very, very small, you will have a very high gain coefficient. Once the intensity starts to increase, your gain coefficient will start to decrease. I will try now. I hope I can make it. I will try to plot this function with you. Now we have, oops, so stupid in drawing actually. So let me make it in a better manner. Okay, let's start with this. Okay, now we have, let's say that this is our y-axis, and this is our x-axis. So here is the intensity, this is I, and here is the gamma. So I will try to make it somehow difficult. So this is gamma, and this is the intensity I. When the intensity is equal to 0, remember the equation, gamma equal gamma node over 1 plus I mu over IS. So when I is equal to 0, you will have a maximum intensity here, which is gamma node. When the intensity here become I S, then gamma will be gamma node, over 2. Then the overall function will be something like that. As far as the intensity increase, the gaining coefficient decreases. That's why it's not an endless process. It's a process that have a decreasing gaining coefficient with respect to the increase in the intensity. So let's now return to our lecture script. So now this is a very, very, very important function. Usually you will find me ask about this function in your final exams and in your home assignments and all this stuff, because it's a very important conceptual function in order to know that why electrons, or why the gain is not an endless process, why this oscillation process is not an endless process. It's a saturation process, as the gain is inversely proportional to the intensity of the system. So let's now turn another term. Someone can say that, okay, I am somehow, I can agree with that, but please remember that in order to reach this equation, this one, you make some assumptions. You say that N2 should be much greater than N1, tau2 should be much greater than tau1, and also you say that here, I think somewhere, yeah, you say that you are now working at steady state, so you put dN2 by dt is equal to 0. That's why you reach this conclusion. What if this condition does not happen? Again, if you remember, I told you, I will ask you only about the mathematical analysis of case number 1. What we are going to do now, which is case number 2 and case number 3, I will never ask you about the mathematics, but I will ask you about the understanding. So now in case number 2, I will say that N1 is not neglected. I mean, I will not assume that N2 is much greater than N1. N2 is just greater than N1, but it's not much greater than N1. So I will write the equation in its exact form, as you can see. I will only apply the second assumption, which is solving at steady state. So I did not make the first assumption, which is N2 is much greater than N1, but I keep the second assumption, which is that the equation is a steady state. Now you have two equations, as you can see. This is still linear equations. Two equations function in N1 and N2, as you can see here. We just rewrite these equations. So now what you can do is that you can solve these two equations mathematically in order to get N1 and N2. By solving these two equations mathematically, these are the two equations, I get R2 here and R1 here, and I write them. By solve these two equations mathematically, again, you are not required to follow this mathematical derivation. You will have these two large N1 and N2 terms, as you can see. Very, very, very large mathematical terms. Okay, doesn't matter. Okay, now let's repeat the same process. We say that gamma equals to sigma N2 minus N1. Now you have N2 and N1. They are a big mathematical term, but we have it. So what we can do is we can substitute N2 here and N1 here, and then we can have the term as gamma. Okay, that's great. So we will have this huge term to express gamma. Again, I will call all this constant as gamma naught, and I will call all this constant except I mu as IS. Then you will have the same equation. So it's again typically the same equation, but with a new gamma node and IS. That's all. But the relation between gamma and I mu is still 1 over. I mean, it's still inverse proportional. So the gain saturation process is still valid. Now I did not apply the first assumption, which is N2 is much greater than N1. I did not apply it, and I solve. I reach the same equations, but with different constants. I just change gamma node and IS, but the equations is still the same. So that means that our equation, our general equation, which is gamma equal gamma node over 1 plus I mu over IS, is still valid, even we did not apply the first assumption. Now let's do the third case, where we will not assume a steady state. We are starting to make it as a general differential equation. Now we are starting to solve a differential equation. Again, this is not required from you mathematically, just the concept is required. So this is the general rate equations, as you can see. But in order to make this rate equation a bit simpler, we will have to make two logical assumptions, which are, we will assume that R1 is equal to 0. Why this is a logical assumption? Let's try to know why this is a logical assumption. Okay, I will return back, please, to the slides. R1 is the rate of injection from 0 to 1. In order to have a laser, you need electrons to move from energy level number 2 to energy level number 1, because this is the only two levels at which stimulated emission can occur. So basically speaking, the injection from 0 to 1 has no meaning. It makes sense to inject from 0 to 2, because now you need the electrons in 2 to drop to 1, and then you have a stimulated emission, and then you have laser. But to inject the electrons from 0 to 1, this is somehow not important. By the way, this happened by chance. You are not intended to make this injection, but this injection happens without your decision, somehow like a noise or an additional effect. So I will assume that this R1 is not so important. I will make this R1 is equal to 0. Another assumption, we agree in the cavity lecture that the input intensity in the cavity may be very, 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 very small and hypothetically, it can be equal to 0. So my second assumption that I will put I mu is equal to 0. I mean that the density is very, 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 very small. So let's now return to the lecture script. And let's also turn the laser and go here. So as you can see, I will put two assumptions. The first one that I mu is equal to 0. The second assumption is R equal to 0. Now, if I put these two assumptions, this now means that we don't have this term, and also we don't have all these terms. And then dn2 by dt is equals to R2 minus n2 over tau 2, as you can see here, and dn1 by dt equals to n2 over tau 2 1 minus n1 over tau 1. These are the two equations we have here. Now, you can solve these two differential equations. Again, for the third or the fourth time, you are not required to make this mathematically step by step. Then you will have these two equations. The first equation is an equation function in M2. And the first is an equation to express N2, and the second is equation to express N1. As you know, from the first slide in this lecture or from the previous slides, that the condition of lasers at N2 should be greater than N1. So what we are going to do now is we are going to start to examine from these two equations if N2 is greater than N1 or not. We will do this mathematically. So let me now return back to the slides. Okay. Okay. We already, okay, so we have these two equations. These are the N1 and N2 equations, as you can see. And what we are going to do now to check if N2 is much greater than N, or is not much greater, is N2 is greater than N1 or not. But we will find that this is actually dependent. If tau 2 is greater than tau 1, you remember the first assumption, then N2 will be greater than N1 all the time. And we will call this as a continuous wave laser. If tau 2 is smaller than tau 1, then N2 will be greater than N1 only in this portion of time. And we will call that as a pulsed laser. So you can have a pulsed laser or a continuous laser based on this condition. If tau 2 is greater than tau 1, or if tau 2 is smaller than tau 1. The issue is now related to the condition. You have a laser whenever N2 is greater than N1. If you put tau 2 greater than tau 1, then you will have a laser all the time. If you will put tau 2 smaller than tau 1, then you will have laser, a period of laser, and then stop, then a period of laser, and then stop, and stop. Or what we can call it a pulsed laser. Okay, so this is the phenomena of pulsed and continuous laser, which is case number 3. Again, for case number 2 and case number 3, you are not required to make a mathematical analysis. Only for case number 1, you are required to make this mathematical analysis. Okay, now I will return back to the question I start with maybe in the first or in the middle of this lecture, which is why we need 3 levels in order to create a laser. In the first slide, we discussed together that in order to make a laser, you have to put N2 greater than N1. Okay, yeah, that's great. So in order to have a laser, we have to have N2 minus N1. But we can ask a very trivial question. From where should I get the electrons in N2? As far as N1 doesn't have a lot of electrons, because I say that N2 is greater than N1, so that means that N1 doesn't have a lot of electrons. So in order to have a huge number of electrons in N2, you should have some stock, which include a large number of electrons, where you can bump the electrons from this stock to 2. And then these electrons will drop from 2 to 1, and then you will have a laser. So this is basically the reservoir. This is basically the ground zero energy level. So when this energy level exists, then you have this bumping and then you have stimulated. Assume that you don't have this energy level, then you don't have this R2, and then you don't have a stuck for electrons. Electrons in 2 will go to 1, and then the condition will not be fulfilled that N1 will become greater than N2, and you will not have a laser. So in order to have a laser, you have to have at least 3 energy levels. A stuck level and 2 energy level where the stimulated emission occurs between. But is the 3 energy level laser is the only laser? The answer simply is no. We have what we can call, a 4 energy level. This is a 4 energy level laser, as you can see. Again, stimulated emission, or what we can call as the laser action, occurs between 3 and 2. Sometimes we call it 1, 2, 3, 4, and sometimes we call it 0, 1, 2, 3. So based on the reference here. But you have a 4 levels. I will keep this for you. I will not go into details, but I may ask about it in the exam. It's actually something for you to understand. I need you to understand, to make 3 very important, or not 3, actually, 2 very important issues. First, try to, or I'm not sure, 3, I'm sorry, 3 important issues, not 2, 3 important issues. First, try to write the rate equation for the 3 energy levels, 4, 3, and 2. Based on your understanding of the 3 energy level laser, try to make the same procedure in order to make 4, 3, and 2. This is the first. Second, try to examine the gain saturation condition based on the very, very simple solution, case number 1 solution, if you remember. Third, try to make a comparison. What is the difference between the 3 level laser and the 4 level laser? These are for you. I will not go into the details of this part. I will keep those for you. Again, you may be asked in the home assignment or in the final exam to make it by yourself. It's the same procedure like we make for the 2 level laser. Okay, let's now turn to the last slide in this long lecture, which was called optical amplification. It's a very, very easy step, just some mathematical steps in order to make us somehow understand a very important issue. Again, I will turn to the lecture scripts. Should be my last turn in this lecture. So again, let's start with this equation. Gamma equal gamma naught over 1 plus I mu over IS. This is that very important. This is actually the core of this lecture, the gain saturation equation. However, as you know, that di by dz equals gamma times I. If you remember, we make it more than 1 time actually. You will find it in the middle of the lecture, I think. Yes, there. Di by dz equals gamma times I. So you can say that gamma equal 1 over I di by dz. Okay, so this is the equation. Gamma equal gamma naught over 1 plus I mu over IS equals 1 over mu di by dz. Simply, you can make a cross multiplication between these two equations. Then gamma naught dz equals I mu, which is this term, multiplied by 1 plus I mu over IS times di. This is a very simple equation. Now it's an integral equation. You can make an integration to both sides. Then this integration over the distance. So we make it from 0 to Lg. Again, Lg is the length of the gaining medium. Gamma naught times dz, 0 to Lg. And equals to, here the integration across the intensity. So I1 is the input intensity and I2 is the output intensity. So we integrate from I1 to I2 in this term. This integration is very simple because we don't have any function of z. Gamma naught is not function in z. So it will be simply gamma naught Lg, only that. Here you have 1 of mu times 1. We will have 1 over mu. The integration of 1 of mu will give you ln. Then it will be ln I2 over I1. And here you have 1 over mu times I mu over IS, and I mu will cancel with I mu. You will have 1 over IS. Then you will have I, which is, I'm sorry, this is a typing mistake here. So it's I2 minus I1. This is the type. So I2 minus I1. Okay. Now I2 is the I1 is the input intensity and I2 is the output intensity. So we can say that I2 over I1 is the gain. Accordingly, we can write the equation gamma node Lg equals to ln gain plus, here I will take 1 over I1 as a common factor, then I will have I1 as a common factor, then I will have I1 over IS outside, and then gain plus. What is interesting in this equation, we have in this equation five important terms. Gamma node, which is the starting gain. Again, please remember, gamma node is the gain at which the intensity is equal to 0. When the intensity is equal to 0, you will have gain equals gamma node, which is the first gain coefficient you will see just after entering the cavity. So this is gamma node. Lg is the distance of the gaining medium. G is the gain. Is is the saturation intensity, and I1 is the input intensity. So knowing these 5 terms, or knowing for any 4 of them, you can get the fifth. So if I told you that I have a gain, a starting gain gamma node equals to blah blah blah, Lg equal to x, I1 equals to y, Is is equal to w, then you can determine the gain you are expecting from this cavity or from this system. This is actually the final equation we will tackle in this lecture. Again, please, my dear students, this is a very, 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 very important lecture. I hope that you make it somehow too accurate. Please, when you are going to study this lecture, please try to study it using your pen and paper, because we have a lot of mathematics, we have a lot of concepts. We have to integrate this concept with mathematics. We have to be good in mathematics in order to understand the concept, and we have to understand deeply these physical meanings in order to make sense with mathematics. Again, thanks a lot, my dear students. This is now the end of lecture number 5. The coming lecture, which will be the final lecture in our course, which is called the Gaussian beams. I hope you enjoyed this lecture, and I am waiting for you in the next lecture, inshallah. See you and goodbye.